Okay, welcome back to the explainer. So we've already spent some time looking at how matrices transform and reshape space, right? Stretching, rotating, tilting, basically whatever the matrix demands. But today we're hunting for a very specific geometric anomaly. We are looking for something that unlocks a whole new layer of linear algebra. I want you to actively picture a grid of arrows pointing in literally every direction. When a matrix transformation hits, most of those arrows are going to visibly rotate to new angles. But take a second and ask yourself, are there any special directions that only stretch or shrink but never bend? Like directions that stubbornly refuse to rotate away from their original line? Well, the answer is yes, absolutely. And they have very specific names. That special direction, the one that refuses to rotate, is called an eigenvector. And the number that describes exactly how much it stretched or shrank along that line, that's its eigenvalue. I'd argue these two concepts are the most important ideas in our entire linear algebra series, mostly because they give us a completely new way to see what a matrix is actually doing under the hood. So, moving into section 1, the equation, unpacking AV equals lambda V. Let's see how all this builds into a single elegant equation. And here it is, A times V equals lambda times V. Let's break down these symbols, because each one is doing some real heavy lifting. A is our transformation matrix. V is that special vector we're hunting for, the eigenvector. And that Greek letter lambda? That's the eigenvalue, which is literally just an ordinary number. What this equation is telling us is pretty remarkable, honestly. It says that applying a full, complex matrix transformation to this one special vector V gives you the exact same result as just multiplying V by a plain old number. For this specific direction, the matrix behaves exactly like basic multiplication. Now, quick bit of housekeeping before we do an example. The rule is that the zero vector is always excluded from being an eigenvector. Mathematically, sure, 0 equals 0, but it's a totally trivial answer. Since the zero vector doesn't point anywhere, calling it a special direction is, well, it's meaningless. So eigenvectors always have to be non-zero directions. All right, let's make this math concrete. Walk through this simple diagonal matrix example with me. In step 1, we have a matrix where everything off the main diagonal is 0, leaving just a 2 and a 3 on the diagonal. Step 2, we apply this matrix to a vector pointing purely to the right in the horizontal direction 1, 0. Now look at step 3. The result is 2, 0. Notice how it's still pointing perfectly in that exact same horizontal direction? It just got twice as long. That means it's an eigenvector and its eigenvalue is exactly 2. So let's pause right here. Based on that pattern we just saw, what do you think happens if we apply that exact same matrix to the vertical vector 0, 1? What eigenvalue do you expect to pop out? Take a second and really think about it. Okay, if you guessed that it stays pointing straight up but gets 3 times as long, you'd be absolutely right. Applying the matrix to 0, 1 gives us 0, 3. So the eigenvalue is 3. Now, you might have noticed that diagonal matrices conveniently hide their eigenvalues right there on the main diagonal. It's a neat trick, but as you can probably guess, most matrices aren't nearly this polite. Usually, their eigenvectors point in really tilted, non-obvious directions. Which brings us to section 2, finding hidden directions, the determinant method. Let's look at how we actually track down these tilted directions. We start by doing a little algebraic shuffling with our original equation. AV equals lambda V smoothly becomes AV minus lambda V equals 0. Then we factor out the V, which gives us A minus lambda I, all times V equals 0. Now, remember that I in there? That's the identity matrix, basically the mathematical equivalent of doing nothing. We just slip it in to keep the dimensions consistent. It makes sure we're actually subtracting a matrix from a matrix, not just blindly subtracting a number from a grid. So here's the absolute crucial point. We already established that V cannot be the zero vector, right? So for a non-zero vector to actually solve this equation, that entire matrix, A minus lambda I, has to be singular. If it wasn't singular, it would have an inverse, and the only possible solution would be that trivial zero vector we just threw out. So, to find our eigenvalues, the determinant of this new matrix must equal exactly 0, which, by the way, ties in perfectly with our previous explainer on determinants. Let's just run through one full numerical example so you can really see the engine working. Step 1, we take a matrix with some actual off-diagonal numbers this time, 2, 1, and 1, 2. Step 2, we subtract lambda from the diagonals and set the determinant to 0. That gives us the quantity 2 minus lambda squared, minus 1 times 1, all equals 0. Step 3, you just expand that algebra out to get lambda squared minus 4 lambda plus 3 equals 0. And finally, step 4, factor it. We get lambda minus 1 times lambda minus 3 equals 0. Boom! Our two eigenvalues are 1 and 3. We literally just found the two special directions for this specific transformation. All right, section 3, the geometric reality. Stretch, shrink, flip, collapse. Now that we've survived the algebra grind, let's see what this looks like physically. So there are basically 4 physical states an eigenvector can experience, depending on its eigenvalue. First, if the eigenvalue is greater than 1, that direction stretches outward. Second, if it's a fraction, between 0 and 1, the direction shrinks, pulling inward toward the origin. Third, and this is pretty wild, if you get a negative eigenvalue, that direction doesn't just stretch or shrink, it flips completely. It points backward along the exact same line. And fourth, if an eigenvalue is exactly 0, that whole direction collapses entirely down to a single point. Actually, let's test your intuition for a second. If a matrix has an eigenvalue of exactly 0, meaning an entire direction in space just collapses to a point, what does that tell you about the matrix's overall determinant? Think back to how we defined our transformation rules. Exactly. A 0 eigenvalue means collapsed direction. And if a direction collapses, geometric information is permanently destroyed, which means the overall determinant must be 0. And of course, if the determinant is 0, the matrix has no inverse. These aren't just a bunch of separate facts you need to memorize. They're literally the exact same underlying truth, just viewed through different mathematical lenses. Moving on to section 4, the honest AI connection. Dimensionality reduction. Let's talk about where this geometry actually shows up in real-world machine learning. Arguably, the single most important application of all this geometry is principal component analysis, or PCA. PCA is this foundational classical machine learning technique used for dimensionality reduction. Basically, it takes complex, messy data and simplifies it down to its most important directions of variation. It does this by looking at a covariance matrix, which is just a matrix that describes how much each feature in your dataset varies alongside every other feature. When you calculate the eigenvectors of that covariance matrix, they literally point along the directions where your data spreads out the most. And the eigenvalues, they tell you exactly how much variance exists on those lines. So, the golden rule of thumb in data science is simple. Keep the eigenvectors with the largest eigenvalues and just throw the rest away. It's a remarkably powerful data compression tool, acting like a filter to remove the noise and letting you focus only on the dimensions that genuinely matter. Now, let's be totally honest about the modern AI connection here. Today's large language models, the massive transformers driving the AI boom, they are not sitting there calculating eigenvectors token by token, not at all. Their forward passes are overwhelmingly dominated by straight matrix multiplication, attention mechanisms, and nonlinear activations. The geometry of eigenvectors and eigenvalues belongs firmly in the realm of classical ML, data analysis, and spectral graph methods. It's incredibly vital for understanding the structure of data for sure, but it is not the engine running real-time LLM inference. Okay, section 5, the big picture, summarizing transformations. It's worth taking a beat here to appreciate how far our geometric understanding has come. Look at how perfectly these 3 core concepts interlock to give us the big picture. A matrix is the transformation itself. It reshapes the space. A determinant gives you the overall scaling factor and tells you right away if the transformation is reversible. And now, eigenvectors and eigenvalues give you the ultimate, fine-grained, direction-by-direction story. They tell you exactly which specific axes the transformation respects and precisely how much it stretches, shrinks, or flips each one of them. But there is a bit of a catch. There's a limitation, quietly sitting underneath everything we did today. This beautiful eigenvector math, it really only works cleanly for square matrices, transformations that map a space back into a space of the exact same size. Real-world data, though, is rarely that tidy. So, I'll leave you with this final provocative thought. What happens when we desperately need this exact same kind of deep insight, but our matrices aren't square? Well, that question leads directly to one of the most powerful tools in applied math, and we're going to unpack the whole thing in our next explainer on singular value decomposition. I'll see you then.